Good afternoon. So first, one announcement. For homework one, we see too many technical problems for people to submit. I understand many of you probably the first time to use GitHub or maybe have problems to register the account with us or something. Yeah, so we have three sections, so three professors we discussed, and we make a decision to say for homework one, as long as you have submitted on time, you will receive full mark. And but the late penalty will be there. So if you haven't submitted on time, so the late penalty will be performed. Yeah, but this will only happen for homework one. Yeah, do not expect this for any other homework. So anyway, the homework one is more try to get you familiar with the GitHub submission system. So as long as you submit on time, at least half of this how say the outcomes we expect from homework one has been fulfilled. So yeah. So today we plan to finish this probability part. Okay. So then from the next week, we will start to talk about higher order functions. Okay. So let's recap a little bit. We have probability functions, but depends on you are thinking about a continuous random variable or a discrete. Okay. We have different ways. For continuous random variable, we will have probability density function. For probability density function, we only care about the area, the size of an area under the curve. Okay. For a particular point, the probability of that point will equal to 0. We don't have interest about that. So to do that, we will try to write, if you have a random variable x, the probability of that random variable take the value between a and b will equal to the integral of this density function from a to b. So basically the area under the curve. Okay. And this is for continuous case, and coupled with PDF, we also have another concept called CDF, the cumulative distribution function. The CDF is trying to essentially, as I mentioned, if you want to say what is this, give you a PDF. Of course, you start with either a CDF or start with a PDF. You have to have either one first. If you have a PDF, then I will ask, okay, what is a CDF corresponding to a particular value? Then what we are talking about actually is the area to the left of that value. So basically, you are adding everything until that small x. So then that value give you is the one which corresponding to the y-axis in your CDF. So which is the reason why we call it cumulative, right? You are accumulate till that point. So which is reason the meaning, the also mathematic formula for CDF will be what's the probability of everything smaller than x. Okay, I hope that makes sense to you. And if you have CDF, then you can take the derivative of CDF to get the PDF. So this is another interesting we talk about. And then for the discrete case, so if you random variable is discrete, like you toss a coin, you rolling a dice, so you will get like a 0, 1, this type of discrete outcomes. It's not like a value which to be continuous, right? So if you have discrete case, then let's say for this outcome, all possible outcome will be 0 or 1 or 2. So for each of them, we can assign a likelihood. Say, okay, for the outcome 0, it will have a quarter chance to happen, half chance happen for 1, and a quarter chance happen for 2. So this will be something we call PMF, the probability mass function. That will be you are counting this discrete outcome, and for each outcome you get a probability value. Okay. So now for discrete case, for individual value, you do have a probability. But for continuous case, as I mentioned, the individual value, you have 0 because you are thinking about shrinking your bin, histogram bin towards 0, right? Remember the density, when we normalize our histogram using a density way, we are dividing by the y's or something. We are counting towards that point, have no meaning for the probability. Okay. So then we are talking about a very interesting case. As an example, this is a uniform distribution. So uniform distribution is essentially to say between a certain range, everything happens equally, has equal chance to happen. Okay. And I do draw a CDF for this. Yeah. So the CDF this is a PDF for a uniform distribution. For CDF, for this, it's very easy, or also very interesting to draw. So first we mark A and B because this is a 2 key point here, right? So then we are thinking, okay, CDF is accumulated distribution or accumulated probability. So then I will think, okay, what happened? What value I should, maybe I should mark 1 here, 1 or 0, because my probability is between 0 or 1. Okay, so what happens for A? Because when things happen to A, we have nothing, right? Everything is 0. So this is 0. So basically for this guy, probably the points for CDF will be stay here. Then I will think for B, because everything happens after B will be 0. So that means there's no outcomes is possible happened after B. So basically when I reach B, I already reach 1 probability. Okay, so the point will be here. Then I will think between A and B, what happens? Because everything happens between A and B has equal likelihood. So my accumulated one will be grow linearly, right? So that makes sense, right? So the line will be this. So everything before A will be 0. Everything after B will be stay at 1. Then this will be things happen between A and 1. So it will like this. Okay, so and this will give you a very good understanding about why you take a derivative of this guy will give you a PDF. Yes, question. This is a continuous. Yes, this is a continuous. Because the discrete is very easy. You have a 0, 1, 2, but this one is like you are every single line along your rear line contribute to your PDF function. Although it's sometimes 0, but they are contributing. So if you take a derivative of this guy, you can easily see it map to this, right? Okay, great. Then the next concept we are talking about is we call empirical or discrete empirical CDF. So this is a very, very important concept. I think it's very useful also. So basically, I give you a bunch of data, and I want to ask you, what is the distribution? Please estimate the distribution. It's difficult, right? Since we do not have much information, we only have those data points. For example, I give you 5 data points here on this corner. We have 5 points here. Then I ask you to draw. Then one key assumption we will make here is the following. Each of those data will contribute equally to your estimation. So basically, if you have 5 points, each data point will contribute 1/5. So this is an important concept here. If you say, okay, that is something better than nothing, right? This is a very good, not the optimal, but it's a pretty good contribution 1/n. Then you will start to what? You will start to adding things. Okay, you will sort your samples from small to large. Then you start to count. If I have negative 1.5 as a first point, maybe I draw here. So if I have negative 1.5, I move my real line along my real line. I see, oh, this is negative 1.5. I will say this contributes to 1/5 to my CDF. I will then, because I have nothing, I have no observation. 0.5, then I will keep stable until reach 0.6, then 0.7. Whenever I meet 1 point, I will add in 1/5. So this will give you an empirical CDF. Does that make sense? The reason I try to repeat this is because this will let you understand what we come to next, the QQ plot. Why we want a QQ plot is because a lot of time I give you a bunch of data, you want to tell what distribution is that. So the typical way to do is you will compute the empirical CDF from those data. Then you will compare the CDF with some hypothesis distribution. You will say, hey, probably this is a Gaussian. I will compare. No, it's not Gaussian. Then I will say, hey, probably this is an exponential. I will compare with. So you can have a way at least to assess, to compare your no distribution model with your empirical one. Once you say, hey, they are looks pretty much very close, then you will say distribution, this data follows this distribution. Then a lot of things will be simplified. You will know what parameter to estimate, and for data which you have no observation, what it may look like. Yeah. So those are the things you can do after you decide what distribution model for the data you observe. But in order to do that, you need a systematic way. So that systematic way will be the QQ plot. The QQ plot, the Q denotes quantile. Okay. The quantile, what is quantile? As I mentioned, mathematically, a quantile is the inverse function of your CDF. So try to remember, try to understand from that perspective. What is a CDF? CDF is say, I give you a X. You want to see what is the area to the left of my X. So basically, everything added along my PDF contributing to that point will be your CDF value, right? So what is the inverse way to do that? The inverse way to say, okay, I want, let me say, if I draw, this is a PDF function, okay. So I want to say, if this area is Q, what will be this X? This will be the quantile interested in this X. He wants to find what X is that will make the area to my left to equal to Q. So this is called quantile. Okay. So like a more familiar concept is a percentile for you, right? If you did a score your SAT or something, then you say, okay, you are scoring in 95 percentile on a test. What does that mean? That means you get a score X that such as the area. So basically, people have lower score than you will contribute to 95. Right. So I hope we are comfortable with this. The reason I try to recap everything is because I think those concepts is particularly important if you are new to probability. So I hope everybody have a reasonable understanding about this topic. Okay. So now I will try to continue with this systematic way to compare two distributions. Okay. It's very easy. If you understand what is the empirical CDF, you will have zero problem to understand this. So what essentially we try to do is, I remember the problem now you have is I present to you a group of data, right? A bunch of data. Then you want to say, what distribution is this? So the first thing is you want to do something similar to your empirical CDF, right? You will sort your data. Okay. Then you will start from small to large. Then for each of the points, you will try to adding 1 over n. Let's say n is your number of samples. Okay. So if you have 100 data, you sort them And then the first guy will become, 10, if you have 10 points, the first guy will be 0.1. Now I will use that 0.1. That 0.1 is what? It's a value in your CDF, right? You say, when you see the first points, which is smaller in your data, and that corresponding to 0.1 probability, right? That 0.1 is a value in your CDF. Then I will try to take that point to the distribution which I want to match, and see in that distribution what is a quantile will give you 0.1. Do you get that point? Then you will take that quantile and see how different is this quantile with your actual data. Do you get that? Then we repeat. We will do the next to the next. So this is essentially the basic idea. So let me repeat one more time. So if you, let's say you have 10 points, then I also try to guess there's another probability distribution. I want to see whether my 10 points fit that distribution. So what I try to do is I will sort my 10 points. Then I will say, using exactly the same way we are doing for the CDF, the empirical CDF. So for the first point, we take it. We will know this first point will contribute 1/10. Then I will say, what 1/10? What the quantile 1/10 in my testing distribution? I will get that quantile, basically get that points which in my testing distribution to say what is that value will give me 1/10 in my CDF. So if my data come from this distribution, these two values, so basically my data points and this quantile need to be very similar. Then I move to my next guy. The next guy will make my CDF to become 2/10, right? Because I have 10 points. Then I will take 2/10, go to my distribution to say, hey, what is the quantile to give me 2/10? Then I will take that point, compare with my data, right? Yes, question.
What sort of threshold is usually used for the difference between?
Yes, that is I haven't come to that part, but it's a very good question. I think but so far, I think I hope everybody roughly know. So this essentially, this picture try to say, we have what? We have a data set QD, the quantile in my data set QD, and also we have quantile with our model. So for the QD, this is my data, right? So imagine you are moved to here. This is probably my first data, my second data, or somewhere. Yeah. So then I will try to say, what is this 0.25 matches in my data and in my model. So basically you will get these two quantile as a data pair. Right? You have two values now. So with these two data pair, you can adding this data pair to a plotting. If they are similar, what you will get? If every data pair is so close, eventually you will get what? You will get a line, right? Think about that. You are plotting a data pair. So each of the data here will contains, let's say, the QM and the QD, right? If these two guys, they are very similar, eventually you will get a y equal to x, right? Yes, question.
So this is the way to compare models that the past be like that.
Yeah, anything, any model you try to compare with, because at the first place you do not know what model to compare, right? You need to guess. Is a Gaussian? Is what? Yeah. So if you guess is right, then eventually you will get something as y equal to x plotting. So this will give you a very clear answer, right? If your data is very away from y equal to x, more or less you will make the wrong guess. Yes, question.
How many quantiles are usually used in generating?
It depends on how many data you have. Yeah. So it is honestly it's not a yes question.
Is there a value for a number you like?
Yeah, you mean the threshold or something?
Yeah.
Is that it depends. It depends. Yeah. So I don't have a obvious answer to that. It probably depends on your application, depends on how many data you have. Yeah, sometimes you are tolerant with some small errors, sometimes, yeah. So, but more or less, if you let's say you have 5 models you try to guess, and you pick the one match your data most, at least this method will give you a very clear answer, right? You can sort the difference. You will say, hey, this is probably it's not the optimal, but more or less is the best I can get. Yeah.
So are you supposed to be able to detect visually?
You can for each one you will get you can compute, let's say, a squared error, right? Then you can compare those squared error to see which distribution match you most. And it's not a complicated methodology, but I hope I have explained this clearly. Did you get it? Yes. Question.
So if we're writing to optimize the Q of the model,
Right.
Optimize the Q, but we're trying all these different models like you said 5 or 6 seconds ago.
Yes, in a toolbox, you can replace the name of distribution. You can generate a few. Yeah.
So those models have internal programs. So
Yeah. You can. I think that I don't know which homework or which lecture we'll talk about those. Yeah. So essentially, in some toolbox, you already have those not normal distribution, those not commonly used distribution being coded there. Yeah, you can compare with. Yeah, this is actually is very important concept. Even now, in more advanced machine learning, for example, in my own research, we are, let's say, in one of the very powerful tool, we are trying to synthesize images. I guess maybe you have seen those. Like if I get your picture, then I see Michael Jackson are dancing, then I can try to simulate how you dance. Yeah. So how those things are try to achieve is actually you are trying to minimize the distribution which in your real data and your fake data is try to align to distribution. So this looks like a very simple idea, but once you really know how to align to distribution, this will give you a very powerful result. Yeah, but this is the basic idea. Yeah. So there, the difference is usually you will have a super high dimension data. You need to align to distribution for very high dimension data. That is a pretty challenge because this is has like single dimension. You are very obviously you will know the probability. You can compare to probability, but when you have, let's say, 1,000 dimension, you don't even know which dimension align with which dimension. Yeah, usually become a little bit more sophisticated. But this is something very interesting. Yeah. Does everybody get this QQ plot concept? Do you need me to explain a little bit more, or are we fine? Yeah. For people who didn't get it, come to my office hour. So Tuesday and Thursday, I will stay in the Zoom. So if you join, I can explain a little bit more. All right. So now let's come to a few very commonly or some very basic distribution. Okay. The first one is a Brownian distribution. So it's super simple but super powerful. So basically, in the Brownian distribution, we care about a binary random variable. So this random variable only have 2 values, 0 or 1. Of course, the obvious example is flip a coin, right? You get the head or tail. So you have 0 to 1. But you can also think about this is a single bit of information. Then this makes this super powerful, right? We all know when we transmit information, you are doing a binary, right? You have 1 or 0. So this maybe can model some information transmission problem or something. Yeah. So it's a very basic. It's a basic for many problems. Yeah. So of course the form itself is very simple. First of all, we have a discrete random variable. We have 0, 1. So we have probability mass function. Okay, right? Probability mass function. Well, the other choice is probability density function, which is not applied here. Right? So we have mass function. So we will have two values. When x equal to 1, what will be that? When x equal to 0 and x equal to 1, what will be that? So, but because you only have two cases, so you only need actually one parameter, which is p, right? Because the other case will be 1 minus p. You adding the two, you will get 1, right? Your total likelihood will be 1, remember, right? So you only need one parameter here, which is p. So sometimes we call p as a success rate. So if you see Bruni distribution, some people say, oh, what is the success rate of this? Usually that will indicate the p. That means, for example, if you think, when I toss a coin, if I get a head, I will get a success. Then the p will be the probability you will get a head. All right. So this is and the figure we draw here, this is a Bruni distribution. It's very simple, right? You have a two case 0, you will match to 1 over p, and you get 1. You have p. So in this case, when you think about Bruni distribution, is to model a coin, but remember your coin is no longer fair. When it's fair, the p have to be 0.5, right? So now my p can be anything. So it's not a fair coin. All right. Yes, question.
What does the tilde mean in that case?
What?
Top right says like x tilde Bernoulli.
Oh, this is to say the random variable follow this Bruni distribution. Yeah. So this is a very common way to write. When you write a random variable, then you do this theta, then you say Gaussian, just to say this random variable follows the Gaussian distribution. The next one is another super powerful distribution we call binomial distribution. So but in the Bruni we have a single coin to toss, but in the binomial distribution we will have n coins to toss. We toss or you say I toss a coin n times. All right. Then I want to ask what's the probability if I get x number of heads. So this is what we try to model using binomial distribution. And the formula is a bit complicated. It looks a little bit scary, but I will explain what does this equation try to say. Okay. So again, I think that I can read a little bit about this. Thinking, flipping a coins n times and counting the number of heads. So this is what I try to say actually. Okay, so mathematically, if we write as a formula, we want to say what's the probability of x equal to small x. The small x is the number of heads, is the particular value of a number of heads when you toss n times of your coins. All right. So now let's see why we have this formula. Okay. So do you recognize? Have you learned this before? Right. The n choose x. So for people who haven't seen this before, what does this mean? This means is if I have let's say I have n coins. What is what is the way to choose x of them out of my n coins? Let's say I put n coins on the table. I ask you to take x of them. What's how many ways you have to take this? Okay. So the way to think why this equal to first of all, the factorial, I hope everybody know this, right? This is equal to n multiply n minus 1 multiplies n minus 2 multiply until 1. All right. So I just try to refresh your memory about the factorial. So if I put n coins on my table, I'll ask you, hey, how many ways you can take x of them? So I will say, okay, first, let me take my first coin. So I have n ways, right? I have n coins on my table. So I have n ways to pick my first coin. Then I will try to get my next. How many ways I left? N minus 1, right? Do you follow my? So you will get my next one. I have n minus 1 ways. Then I have n minus 3 coins left. So I have n minus 3 ways to take my third coins. Since I will be satisfied if I get x coin in my hand. So which is reason I will have m factorial divided by n minus 1 factorial ways to pick, right? I hope everybody follow this. Yeah, and then since I do not really, I only care about I have X coin in hand. I do not care about the order about these X coins. So no matter how you order them, I do not care. And how many ways I have to order these X coins, which is X factorial. So I divide by X factorial further to remove the order. So to show I only care to have a set of X coins. I do not care about their orders. So which is reason this is how this we arrive at this binomial coefficients. So this is just try to say, hey, there's if you have n throw coins n times, I have n choose x ways to pick the subset to claim, in order to claim them to be head, then I need to say p raised to power x, because for each coin you have p probability to be head. And so you have p raised to power x to say, hey, these x coins are head. And then the remaining, each of the remaining guy will be the tail, right? So how many remaining guy you have? N minus x. For each of them, you have 1 minus p chance for them to be tail. So this is how this formula arrives. Yes.
This only works when there's two outcomes, right?
Yes, yes. Yeah. If you, of course, if you have a more, that is called multinomial. Yeah. So we probably will see that in the later part of this class. So basically, for that one, for that case, you are instead of p minus p, the only difference is what you will have p1 raised to power x1, p2 raised to power x2, and then you need to change a little bit of this guy. Yeah. So, but in in machine learning, a lot of time we probably will throw away the coefficient. Then you are remaining with a that is actually very related to one section we will talk later. Is like a knife-based classifier. We will talk about this. A very good question. Are we fine with this binomial formula? Are we okay? Yeah, but anyway, remember the formula, and then think about my analogy to say pick coin. And actually, this is a very, very useful mathematic observations. Yeah, to say how this binomial comes. Yeah. So now let's see one example. We are interested in model whether a machine produce outcomes in spec or not. So then we collect 200 samples and find 20 out of spec. model the next output as a random variable, what is a PMF function. So what does that? When you see this real world, although it's a toy example, but it's mapped to some real world scenario, right? So you will say, hey, I have learned some distributions. Obviously, you have only learned two distributions so far, so probably one of them will be work here. So which distribution we will use to model this case? Yes, exactly. Okay. So now our scope are narrowed to Bruni now. We have one choice now. So first, what is a success rate? What is a P here? Right? Yes.
0.9.
Yes. Fine. Yeah. Yes. Yes. Exactly. And so this is the answer. Let's go through the answer together. So we will use x equal to 1 denotes 1 in spec and equal to 0 denotes out of spec. So since we know this is a Bruni random variable, so we will first compute our success rate as 0.9, as this gentleman say. Then we can easily write the distribution, right? This will be our PMF. And if you like, you can also, based on the definition, you can try to do what is a CDF in this case, right? I hope this makes sense. Although it's very trivial, but you, based on the definition, you can still do that, right? All right. Okay, this is a most exciting distribution, is a Gaussian distribution. The reason why Gaussian distribution is so powerful is probably the most important distribution. Okay, I think that I have mentioned before. It has the PDF of a Gaussian. It has this bear form, bear shape. Yeah. The reason why the Gaussian is so powerful is because in the later of this class we will see something called, for example, the law of large number. So essentially, that is trying to say is that if you let's say I measure the average height in this class, okay, then I go to another class, I measure again your average height, then I measure again. So I don't even need to know what is the underlying distribution of your height. I don't need to know. But then what I will know is that this average I pick from this class, from that class, I take sufficient. Those will form a naturally form a Gaussian. I think that this makes sense, right? Because no matter how, eventually you will have most of your heights fall around certain values, right? Let's say 1.7 meters or a reasonable value. Then those guys who are super tall, let's say 2.5 meters, of course, is much less. They were mostly around here, right? And those guys are super short will be around here. So most of people will be for among the center, right? So this is a very make a lot of sense, right? This type of Gaussian distribution. So in order to model the Gaussian distribution, we need two parameters. One is a mean. The mean is the center. What is this is the mean. Okay, the center. So let me rejot it. So this will be your mean. And also there's a variance. The variance is a concept to measure the spread, because you need to know where the center of distribution is, right? The other one is what the shape of your bear shape, right? Because I want to know how spread. Because what I know is if you integrate over the area is equal to 1, right? So I only can control is how do you spread my the total area. Does that make sense? So this variance will be, we will see how to calculate the variance. The variance is actually we will compute is give you a lot of samples. You will, if I know what is the mean, okay, I will see how far away, what is the average way those samples are deviate from my mean. So in Gaussian, there's a very cool property about talking about the spread or talking about the variance. This is something we call 3 sigma rule. I don't know if you be aware the variance equal to sigma raised to power. This is variance. The sigma here is called deviation, standard deviation. Okay. So what we know is there's a 68% of points will be plus minus 1 standard deviation away from your mean. So that means this area will contribute to 68%. All right. And then 95% of points were within plus minus 2 sigma. That means this area will fall into 95, and then 99.7% of the data within 3 sigma away from your mean. So that means this is 3 sigma. This area 99%. That means very, very tiny amount of data points will fall 3 sigma away from your mean. So this is one of very useful property when later we cover talking about the, let's say, hypothesis test. We will, based on this, try to reject or accept some of the hypotheses. So, for example, you infer certain things which is many sigma away from your mean. So it was less likely that your guess is right. Yeah. So this is a basic idea. It's very useful, 3 sigma rule. And yeah, also remember those values, because remember during when we do exams, and often we do not wish you really calculate a lot. So a lot of times we will try to make the 3 sigma rule, assuming you know this. Okay, so then you will do not need to calculate a lot. Yeah. So 3 sigma rule is important. It's useful to construct confidence interval and hypothesis test. There's one more very interesting distribution we want to talk. Of course, there's many distributions. We don't want to like, this is not a probabilistic or statistic class, so we don't cover too many, but this is probably one of the last. It's called exponential distribution. The PDF of this distribution, exponential distribution is something that looks like this. Okay, it's like exponentially decay. All right, the form is the mathematical formulation of this PDF is, say, if x smaller than 0 is equal to 0, so nothing happens on the negative region. So nothing happens here. The only things happens is in the positive region, as you can see. So only when x greater or equal to 0, then I will start to have this formulation. So I hope everybody recognize E, right? E is a value 2.7 or something. So E is a value and is a constant. E is a constant. So what we only remaining is a lambda. So basically, we only have one parameter here. It's called lambda. Lambda is a rate parameter. Okay. So we all know the exponential distribution, exponential function is something looks like this, right? Exponential. Then we have a negative in this here. So that means we will have something like this shape, right? So which is reason we have something like this. Then you're using lambda to control how fast or how slow. The reason why this is very important, of course, this is probably out scope of this the class, but we often use this to model, let's say, the inter arrival time, occurrence of event. Why? The reason is because this is something we so-called the memory independent. So basically, your next customer come visit my shop is independent from when the last customer arrived. So if you're interested, you can go back to try to dig a little bit into to say why we care about the memoryless property of this. So which make this a very good model to model those, for example, inter arrival time, which is a very common things you want to model, right? So the next is an example. I think we hope we can complete this example. So let's imagine the time between the visit to a website measured in minutes is exponential distributed with a rate parameter lambda equal to 2. So find the CDF of this random variable, and what is the probability that there's more than 0.5 between visits. So first of all, find the one information we have here is we were going to have a exponential distribution, so we can plug in our exponential distribution with a rate equal to 2, right? So we naturally will have a probability density function. Then we probably need a little bit of calculation to integrate, to do the integral, to calculate the CDF, right? After you have CDF, then I give you a point, let's say 0.5 minutes. That is what? That is probability for anything smaller than 0.5. So basically, your CDF for 0.5 that measures events has less value than 0.5. But we are asking about more than 0.5. Then probably you need to using a 1 minus this guy to look at the other side, right? So this is probably the way we are thinking about. Because I don't have much time, so I give you less time to think. So I just tell you, but we go through the calculation here a little bit. So first of all, we plug in the lambda equal to 2 into the formula. So we will get this guy. This is nothing, it's just plugging the lambda. Then you need to calculate the CDF. So this is something I hope you will go back to even do some calculation. If I want to integrate from negative infinity to x, plugging this guy, you will get this, because anything below 0 equal to 0. So I don't care. So I only care about I only care this guy. So I will do 0 to x, I will integrate this. And if you, with the calculus 101, you know how to calculate the antiderivative, right? So you will get this guy, right? Because if you don't trust that, you can take a derivative. You can take a derivative of this, you will get this. Yeah, so you can do a calculation and go back. Then now I will plug x into this guy minus plugging 0 into this guy. When you plug in 0, this is 0, this is 1, so you get -1. And you plug in x, you will get this. And then you minus 1, you will get 1 minus e raised to power -x. If you don't trust me, go back to calculate. I do, even you trust me, go back to do your calculation. This will be your CDF. But I ask you about things the other side of your CDF. So CDF is P, the CDF is Px smaller. This is what this guy give you. So if you want to compute the greater, you need to using 1 minus. So then you plug in, you'll get this. Go back to calculate. If you cannot reproduce, let me. So I see you next week. Yeah, also someone need me to sign a form, I remember. Is you? Who are, someone need me to sign some forms?
No?
No?
I have a question.
Okay.